Excellent, excellent. So we're going to start with the concept of impulse and momentum. And I want to begin by trying to give you a definition of momentum, even though I may have done this last week, but I didn't do it in both classes, so I can't remember which is which. We define momentum as inertia while moving. And although it is very similar to energy in some respects, there are key differences. First, how we calculate it. We use the symbol lowercase p. The bar comes back out because momentum is a vector quantity. That's the first thing I want to emphasize that's different between momentum and energy. So I'm going to put energy here and momentum here, and just discuss, when I say energy, I mean kinetic energy. I just want to discuss a few of the major differences. First, energy is a scalar. That's why the V is squared. It takes away any information about the direction of the object. Momentum is a vector. It is clearly about direction. We can't really understand the motion of an object without understanding both, but momentum has less emphasis on velocity. Where kinetic energy is velocity forward. Double the velocity, you only double the momentum. Double the velocity, you quadruple the energy. So there's a big difference between the two and how they deal with changes in velocity. The last thing that I want to be very clear about is both of them have a similarity in that they are only changed by an unbalanced force. So that goes for both of them. And this is true whether we're talking about a single object or a collection of objects. So in your notes, please put that in there. This is true whether we talk about a single object or a system of objects. Because with momentum, we'll be talking more and more about the center of mass of a system. And so we'll have to consider collectively what that means to the entire system's center of mass. Now, a little bit of a station kind of keeping stuff that you need to know. Let's talk about the units for a minute. The units for momentum are kilograms, meters per second. There's no special name for that unit. So whenever you write out the units for momentum, you just write all of that out. So we don't call it anything special. Also, because it's a vector quantity, and because we use lowercase p, I don't really know why we use lowercase p, probably because m was already used for mass, but make sure for the time being that you are putting the bars on top of the symbols to emphasize for you that direction is incredibly important when it comes to momentum. We spent the last 3 weeks dealing with energy where direction didn't make any difference at all. It's very much center and forward. In fact, studying momentum is as much about vector problems as it is about dealing with the math that we would normally deal with for like any kind of kinematics problem. This is for you guys who are in AP Physics 1. Last year, we just did a cursory look at momentum. This year, there are some deeper ideas, so I don't want you to throw away, like, oh, I just have to listen because we're not doing this, we're doing all the same stuff. There are some deeper things. You'll have to do two-dimensional momentum. In AP Physics 1, you'll only have to do one-dimensional momentum. So all the things we deal with, we'll have to deal with in 2 dimensions. And so I'm going to do a couple of examples today just for some simple stuff to kind of emphasize that. So I want to make sure you guys who are in AP Physics 1 don't just kind of tune out. So pay a little closer attention than you normally would. So let's start with how we change something's momentum, and that's the word impulse. Impulse is defined in 2 parts. There's the cause of impulse. Let me move this over someplace else. There we go. There's the cause side and the effect. Now, impulse itself has a symbol. I don't use it usually. I think it's a capital J. I just usually write the word impulse, but I think the symbol for impulse is capital J. Impulse is defined as the change in momentum, and therefore is itself a vector quantity. meaning impulse has a direction. But it doesn't have to be in the direction of the impulse. It's in the direction of the change in the impulse. And that's important. I would put that in there. This is a vector that points in the direction of the change. So it doesn't necessarily point in the direction that the momentum of the object has. It points in how the direction of the object, the momentum of the object is going to be changing. So if your object is traveling forwards but it's slowing down, then that change is going to be backwards. But if that object's moving forwards and is going to be moving upwards soon due to this change, well, that means that the change in momentum might be at an angle. So one of the things that you have to consider, and that's going to be a big part of our next test, is understanding the directional change of momentum. And also how we cause a change. And we cause a change using force. But for this class, it's going to be a little more complicated. Although this is not the definition you'll have to have for this semester, this is technically what's going to be on your equation sheet. So let's start with that. Technically, this is the definition that we're going to use for impulse. It's an integral. And it has lots of similarities to work. If we consider our similarities to work, there's a bunch. First, the original definition of work that we didn't use much because we're not using much of the algebra yet, or calculus yet, it was an integral as well. It was a force applied over a displacement, and we assumed that that force might be at an angle and that that force might be changing as it moves across the displacement. So we had a dot product here, vector information here, but remember, work was a scalar. If this was done by an unbalanced force, then that could lead to a change in kinetic energy. So impulse has a lot of similarities. We're dealing with an unbalanced force. If a force is applied to an object over some period of time, it will change the object's momentum. Now, just a brief aside, the truth is Newton didn't actually formulate Newton's laws the way we teach them to you. Newton's laws always had momentum in them. In fact, Newton's second law is supposed to be written as the rate of change of momentum. This is the way Newton's second law is supposed to be written. It's a direct extension of what you see here to the side. And there's some important details here that I want you to pay very close attention to. This is a derivative, but you guys have made it through our first quarter, so you understand that this can be written as the deltas if you're dealing with a force that has a constant change in slope or a constant slope. So that suggests quite clearly that if you plot momentum and time, the slope of that graph is going to be the unbalanced force. So first, a momentum versus time graph can tell you the force applied to the object. And that'll be the slope. We don't do much graph work anymore, but we need to be prepared for graphs that might show up on the exam. So the slope of a momentum versus time graph is the unbalanced force. In addition, if we multiply both sides by delta t, we get delta p equals F times delta t. Now this is the algebra version of impulse, with the right side being the cause side and the left side being the effect side. So then cause, effect. So for this quarter, in the last couple of days here, when we calculate impulse, we're just going to take the force and multiply by the time. But this assumes we're dealing with an unbalanced force. The change in object's momentum, the force has to be unbalanced. So we don't have to worry about what we did with work. Remember, with work, we had to calculate the force, the work from each force. We're not doing that here. We're saying the only way to change something's momentum is through an unbalanced force, period. It's based directly on Newton's second law. So this has only unbalanced force built into it. So unlike work, where every individual force could do work on the object, both giving it energy and taking it away, with momentum, we only talk about the unbalanced force. If there's an unbalanced force, you can change the object's momentum. If there's not an unbalanced force, you can't. It's more straightforward and more absolute. You know, you don't have to worry about what all the other forces are, what direction they're acting, or anything like that. There's no dot product here. There's nothing to deal with vectors. The direction of the change in momentum is the direction of the force, because time is a scalar. So we're just multiplying by a time, which is a scalar. But also that suggests that if you plot force versus time, so if we have some plot of force versus time, doesn't matter what it is, the area under this curve will be the change in momentum. So two things connected to graphs that deal with impulse. All right, we all got that? Now, I'm not going to throw a whole lot of graph practice at you, but you should probably be prepared for a multiple choice or two test question. So I'll make sure that we've seen a few that you guys will be able to appreciate, but I'm not going to work on that right now. I want to keep talking about what this is actually currently about. So I have something I've set up. I got to find it. There it is. This will be the same example I use every year because I think it's pertinent. Everybody in this room, I am sure, has eventually at some point or another dropped something, their phone, a glass, something, and it's broken. So, although it sounds like one of us dropped our phone and didn't break it. Good job. Good job. Now, if I take two glasses and I drop them above the floor, can we agree with the following couple of statements? I'm not going to write these down, but you should probably think about it. Can we agree that they will both be traveling the same speed when they make it to the floor? They're dropped from the same height. They should make it to the floor at the same speed. Does everybody understand why that's true? I would say conservation of energy is the best example, right? They have the same amount of potential energy, and therefore when they make it to the floor, they'll have the same amount of kinetic energy, so they should be traveling at the same speed. So if I take two glasses, drop one of them above carpet and one of them above a tiled floor, they'll make it to the floor at the same speed. That's important because the floor is going to stop them. Agreed? So that means both glasses will have the same change in momentum because they're going to reach the floor at the same speed and they're both going to be brought to rest. So their P final is going to equal 0 and their P initial is going to be equal to mv, where this is what they get from accelerating downward. So is it clear from just that statement that delta P above tile has to be equal to delta P above carpet? Does everybody understand the argument I'm making? And do you have any question about that? Which glass likely breaks? The one above tile. This one likely will shatter. This one has a good chance of surviving. You guys agree with that? So this one survives. Spell it correctly, survives. There we go. Which one experienced the greater impulse? The one above tile or the one above carpet? The definition should be right in front of you. They have the same impulse. Both glasses experience the same impulse. Right? So that's the first thing I want to point out. Both glasses are brought to rest. So if I'm trying to trick you, that was the trick, because they have the same impulse. But one of them shatters, and that's because of the cause of the impulse. The effect is that the tile and the carpet both bring the glass to rest. But the thing that's about impulse has to do with the other part, the cause. In both cases, there was an upward force on the glass from the floor, a normal force, acting on the glass from the floor. They both experienced the same impulse, so force times time had to be the same for both. But which one stopped sooner? Probably the one that shattered. Yeah, the carpet is cushy, right? What you would describe as a soft landing actually is an increase to the amount of time it takes to change something's momentum. By increasing how much time it took to change the glass's momentum, we decreased how much force was necessary to stop it. It's the same reason why on the tiled floor, we decreased the amount of time it takes the glass to stop. That has to increase the amount of force necessary to stop it. It wasn't impulse that broke the glass. It was force that breaks the glass. If you apply enough force to the glass, it will break. You can reduce that force by taking longer to make the object's momentum change. This is seatbelt week, right? Isn't that what they just said on our intercom? If we think about that for just a moment, that is what supplementary restraint systems do. Your seatbelt is the first thing to stop you if you're wearing it. If you're not, what's the first thing to stop you? I'm not a baseball fan. Is anybody here a baseball fan? Nobody? Not one? Oh, okay. Maybe this isn't a good example. How about boxing? You guys like boxing? I got 2 or 3. Now, I'm not talking UFC, but it will work. But like boxing, with the gloves and all. So, and I won't ask this question, but there you are. You're a boxer. And all right, you have some choices here, right? Boxer's going to take punches. If you don't know how boxing is scored based on the number of punches that you land, successful punches. Boxing is scored like any game. You usually don't see the score. They don't put it usually up on the screen anymore. Sometimes they do, but not very often because multiple judges are watching the boxing match at once. And although you might, if you don't watch boxing, you might think the whole idea is for somebody to knock somebody out, knock them on knock them on the ground. It's not exactly it. Although it is true that you can get a TKO by knocking somebody onto the mat 3 times. The most boxing, and I mean most all boxing that you watch, they don't get knocked out. They score points. There's lots of boxing matches before the big ones that make it on television. So if you're going on the circuit and watching boxing, most of the time it's a point out. It's how many points they score. Multiple judges are watching, and a point is hitting the face, or a point is hitting the chest or the body. So those are your points. And the more points you land, the more punches you land, the more points you earn. If you're a boxer, you know you're going to take some punches. And the idea, when a punch is thrown, you're going to stop that punch one way or the other. Now, you can stop that punch by leaning into it, or you can stop that punch by leaning away from it. Which one's going to take the punch longer to stop? Leaning towards it or lean away? Leaning away, sure, because you're already moving in the direction the punch is going. It's going to take longer for the punch to be brought to rest. So if you ever watch boxers, you see how they're always bobbing and weaving around? That is because they know they're going to take a punch, and they're going to try and reduce how long it takes for that punch to stop. In fact, they're also going to put Vaseline on their cheeks, so maybe the glove will glance off, and that means the person who throws it has to exert their own force to stop the punch, which means wears them out even longer. The whole idea here is to reduce how much force you're going to take so that you can return and strike your opponent. So if you watch boxing matches, especially the lighter weight matches, like featherweights or middleweight matches, they throw hundreds of punches per round sometimes. And it's all in the service of trying to score points. And they know they're going to receive their share of punches. And they try to block them, and they're going to do the best they can to block them as much as possible. But that still means taking a punch. If they block it, they're just blocking it with their arms. And that means taking that punch in the arms. But of course, if they take it in the arms, it doesn't count as a point. So again, all of these are about adjusting how much force you're going to experience at the expense of how long it takes for the object to apply that force. This is how you cheat in baseball. I'm going to still use my baseball example because I like it. Do my best to draw a baseball bat. Look like a baseball bat? Good enough? A little exaggerated because I need to be able to draw inside of it. Cheating in baseball goes back a long way. Believe it or not, there's been congressional hearings on cheating in baseball because I guess Congress had to deal with it. That was something in my history. So back in the 90s, they brought baseball players who were juicing, into court to talk about their experiences using metabolic steroids. And to be honest, baseball was more fun then. There was a lot more home runs because when these guys were juicing, they could really hit the ball hard, and they were constantly putting it over the fence. The game was very exciting. They can manipulate the game at any time. They do so all the time. Manipulating baseball isn't just about changing the rules, although they do change the rules from time to time. They manipulate things about the game. Now, if you're not using steroids and you're working out all you can, eventually you're going to reach a limit. That's how strong you can get as a baseball player. One way you could increase your chances of having a better connection with the ball and therefore have a better, make the ball travel further is, remember, this whole arrangement is about two things: the force you apply and how long you can keep that bat in contact with the ball. Now, bats are highly regulated in baseball. I mean, they're inspected, they're regulated, they can only be a certain mass, they have to be made out of a certain type of wood. That's why a Louisville Slugger is one of the most common bats that's used in baseball, but they are a regulated product. They all have to use the same bat. They can use slightly different weights of the bat, but they're all supposed to use the same bat so that everybody's level playing field. But if you cut the top off the bat and you hollow the inside out, you can fill the bat with a softer material. Now, usually to do that, if you fill it with a softer material, you also lighten the bat. So since the bat is going to be measured to make sure it measures the weight it's supposed to, you used to have to put something inside the middle of that, usually a metal core that you would wrap the cork around. Then you put inside the bat. Then you would glue the top back on carefully to make sure the wood grain shows, and sand it back down so it matches. Corking the bat. What does it do? It increases how long the bat's in contact with the ball. It doesn't change how much force you apply, but if you increase how long the bat's in contact with the ball, you increase the change in momentum of the ball. Corking the bat was a way for you to be able to hit the ball faster without actually getting any stronger. It's cheating, but it worked until the bat explodes and everybody finds out you're a cheater. Baseball does it on their own. If you know anything about the ball has an outer cowhide that is dyed under a process, so all the balls are the same. It's got the stitching. The stitching is there not just ornamental. The stitching is there so that the pitcher can grab the ball and make sure they spin it when they throw it so they can get the ball to dance through the air. But if you take that off, you'll find that it's wrapped with what looks to be lots and lots of string. It is. There's a string around the outside that's wrapped around the outside of the ball, but then in the inside center of the ball, there is a rubber core, some kind of synthetic plastic. You can make the ball spongier just by increasing the size of that core. So baseball does it all the time. They manipulate the ball in the service of the game. You want to make the game more exciting? Well, you can just make the ball go farther every time people hit it. That's why records in baseball often get contested, and people talk about, well, they changed the ball again. So do these new people who are making all these records for hitting home runs, do they count against the people who did it before? So these are changes that all sports go through to try and evolve the sport. And the same thing happens in golf. They manipulate the ball all the time. That's why the ball is tightly regulated, so everybody's hitting the same kind of ball. And although certain manufacturers are allowed to make the ball, the inside of the ball is still very similar. It has a kind of a neoprene outer coating, and then on the inside there's going to have some kind of elastic material in the middle to try and ensure that the ball can go the distance that they suspect it should be able to go for the field. Most of the manipulation of golf balls has to do with the dot pattern on the outside.